About Hello friends, we will discuss about density based viscometers, which are the second type after capillary based viscometers. Now density based viscometers are of two types, falling sphere viscometer and rising sphere viscometer. The example of falling sphere viscometer is Hoppler viscometer, whereas the example of rising sphere viscometer is bubble viscometer. So this is diagrammatic representation of falling sphere viscometer, which consists of a burette kind of structure. So in the burette, the liquid is filled. 2 points are marked in the burette, point A and point B, and a spherical ball made up of steel or porcelain or glass is allowed to fall. First, we use standard liquid. We test the rate at which ball moves from point A to point B. We determine the time. Then we change the liquid with the test liquid, so we can use both standard and test liquids. So first we do the experiment with standard liquid, then we do the experiment with test liquid. Similar to capillary based viscometers, they only give us information about relative viscosity. No absolute viscosity determinations can be made. They can be used for viscous materials like glycerine, but only Newtonian materials. Non-Newtonian materials are not tested via density based viscometers. So we come on to the theoretical part, that when ball or sphere is allowed to fall freely under the influence of the material or liquid, Stokes' law comes into play. So Stokes' law is the law which governs rate of sedimentation usually. Viscosity is equals to d square rho s minus rho naught into g into t divided by 18 into v. If we see these parameters, d square is diameter of the ball, g is acceleration due to gravity, t is time taken from point A to point B, ball to move from point A to point B, rho s is density of ball, rho naught is density of liquid which we are using, V is volume from point A to B. Fine. So if we see all these things, d square is constant, g is constant, rho s is constant, and 18v is constant. So equation again changes to, so constant is indicated by k. So neta is equals to k into rho into t, where rho is density and t is time taken by ball to move from point A to point B. Now what we do in experimental part, we fill it first with the standard liquid, determine the time and density via specific gravity bottle. Then we use test liquid and determine both density as well as time taken from movement from point A to point B. So equation again becomes as the previous equation. It is rho 1 T1 divided by rho 2 T2. Fine. Now what is the basic principle? Basic principle is Stokes' law, which is further governed by viscous drag. So when ball starts moving, first of all it moves down because of its weight, but suddenly it stops moving due to viscous drag of the material. Soon both of them become constant, and then material start flowing with a constant terminal velocity given by Stokes' law. And based on that, calculation is made and experiment is done. So this will help in determination of relative viscosity of viscous materials such as glycerine, such as syrup, but only for the Newtonian materials. Now the second is, this is falling sphere. The second one is rising sphere, which the example is bubble viscometer. So to understand it, we can take 10 tubes. So one tube is say our test tube, and remaining 9 are standard, filled with the liquid of different viscosities. So say from 1 to 9 different viscosities are there. So hypothetically 1, 2, 3, 4, 5, 6, 7, 8, 9. So they are filled such that a small amount of air is remaining, and then in the 10th tube we will fill our test fluid, and a small amount of air is remaining in this also. Then we invert whole of the stand. When we invert whole of the stand, then bubble is formed at the bottom and it start to rise up. We have to check that our test material bubble is coinciding with the rate, means time taken by bubble of test liquid to reach to the top, and we check this time with all other standard solutions. So in that case, suppose it is coinciding with the fifth, so this means that velocity of our fluid is same as that of velocity of that fifth fluid. So this is again relative viscosity determination, and the apparatus is known as bubble viscometers. Although bubble viscometers are not widely used, in the lab also we are using falling sphere viscometers.